Look up into the clear, dark expanse of a moonless night. What you are seeing is a portrait of infinity, a silent, glittering testament to permanence. For all of human history, we have looked to these same patterns, these same celestial diamonds, scattered on black velvet. They are our anchors in the cosmos, the silent witnesses to our fleeting existence. The hunter Orion, the steadfast North Star, the river of the Milky Way. They were there for the first humans to walk the earth, and they are here for us now. But this permanence is an illusion. It is the grandest magic trick in the universe, a deception created by the unfathomable slowness of cosmic time. The night sky is not a static painting. It is a living, breathing, evolving entity. Its occupants are not fixed. They are travelers on an impossibly long journey. Tonight, we journey into the deep future and the distant past. We will watch stars be born in fire and die in glory. We will see the familiar constellations of our time warp and dissolve into unrecognizable patterns. We will learn that the sky you see tonight is unique to your moment in eternity. Prepare yourselves for a voyage through the secret motion of the heavens. The story of why you and no one who comes after you will ever see the same night sky forever. The human heart beats, on average, about 80 times a minute. Our lives are measured in these fleeting moments, strung together into decades. We perceive the world through the lens of this rapid, urgent rhythm. A season is a significant passage of time. A year, a major milestone. A lifetime, the entirety of our known existence. Against this frantic tempo, the stars seem eternal, unmoving, unchanging. But the universe operates on a different clock. Its heart beats not in seconds, but in millions of years. Its seasons are not marked by the tilting of a planet, but by the birth and death of suns. To the cosmos, a human lifetime is less than a single breath. This is the secret to its illusion. The stars are not still. They are simply moving in a time scale so grand that our lives are too short to perceive it. Imagine you are a single, stationary microbe, living for just 1 second on the hour hand of a giant clock. For the entire duration of your existence, that hour hand would appear to be a vast, motionless, and permanent fixture of your universe. You would be born on it, you would live on it, and you would die on it, and it would never have moved a perceptible amount. You would have no reason to believe it was ever in motion. We are that microbe, and the night sky is that colossal clock hand. The stars are all moving, some at incredible speeds, but they are so profoundly distant that their movement across our sky is imperceptible to the naked eye over a single lifetime. It is a motion so stately, so patient, that it has taken us centuries of careful observation to even begin to measure it. Consider the Big Dipper, one of the most recognizable patterns in the northern sky. Its stars look as if they are fixed in their familiar shape, a permanent celestial ladle, but they are not a true family. They are a temporary alignment of unrelated travelers, all moving on their own separate paths through the galaxy. The two stars at the end of the Dipper's bowl, Dubhe and Merak, are moving away from us, while the stars in the handle are generally moving together in a different direction. They are like a group of runners on a vast field, seen from a great distance. For a brief moment they might appear to form a distinct pattern, but give them time, and they will inevitably drift apart, and the pattern will be lost forever. This concept is the key that unlocks the secret life of the night sky. To see the stars as they truly are, we must learn to think not in human time, but in cosmic time. We must accelerate our perception to see millennia pass as seconds. Only then does the static, frozen museum of the night sky melt away, revealing its true nature, a dynamic, violent, and ever-shifting celestial river. And the first motion we must understand is not of the stars themselves, but a secret motion of our own planet. A slow, silent wobble that is rewriting the heavens above us. For millennia, navigators and explorers have looked to a single, unmoving point of light in the northern sky, a celestial anchor in a sea of moving stars. We call it Polaris, the North Star. While other stars rise and set, Polaris hangs steadfast, dutifully marking the direction of true north. It seems to be a permanent fixture, a special star chosen by the cosmos to be our guide. But Polaris's reign as the North Star is a temporary appointment. It is a celestial crown that is passed from one star to another over vast spans of time. The reason for this change is a motion of our own planet called axial precession. Imagine a spinning top. As it spins rapidly, its axis is perfectly upright. But as it begins to slow down, it starts to wobble. Its axis of rotation begins to trace a slow, lazy circle in the air. Our Earth is that spinning top. It spins on its axis once every 24 hours, but it is also being gently pulled on by the gravity of the sun and the moon. This gravitational tug is not strong enough to knock our planet over, but it is enough to make it wobble, just like the top. This wobble is impossibly slow. It takes the Earth approximately 26,000 years to complete just one single circle. This means that our planet's axis, the line that runs through the North and South poles, does not point at a fixed spot in the cosmos. Instead, it slowly, majestically traces a great circle across the heavens, and whatever star happens to lie along that circle becomes our North Star for a time. Right now, our axis points almost directly at Polaris. It is a cosmic coincidence, a happy accident of our current place in this 26,000 year cycle. But it was not always so. When the ancient Egyptians were building the pyramids, around 4,800 years ago, their North Star was a different, fainter star in the constellation Draco, named Thuban. They aligned their magnificent structures to this star. For them, Polaris was just another insignificant point of light, far from the celestial pole. And as the procession continues, Polaris will slowly lose its title. Over the next few thousand years, it will drift further from the pole. By the year 4000, a star called Gamma Ceve will begin to take over. By the year 14,000, the brilliant blue-white star Vega, one of the brightest stars in our summer sky, will become a spectacular North Star. Our distant descendants will navigate by its light. They will tell stories about it. For them, the idea of Polaris being the North Star will be a historical curiosity, a relic of a past sky they can never see. This grand planetary wobble is our first clue that the sky is not a fixed map. It is a shifting canvas, and our perspective on it is constantly, if imperceptibly, changing. But this is only the motion of our point of view. The stars themselves are on an even grander journey. They are adrift in the cosmic ocean, and their own motion is slowly tearing our familiar pictures apart. In the year 1718, the English astronomer Edmund Halley, the same man famous for the comet that bears his name, was meticulously comparing his own modern star charts with those of the ancient Greek astronomer Hipparchus, compiled nearly 2,000 years earlier. He expected them to be identical. To his astonishment, they were not. He noticed that a few of the brightest stars, Sirius, Arcturus, and Aldebaran, were not in their predicted positions. Their locations had shifted, just slightly, by about the width of the full moon. The shift was tiny, but its implication was monumental. The fixed stars were not fixed at all, they were moving. He had discovered what we now call proper motion. Proper motion is the apparent movement of a star across our line of sight, caused by its actual velocity through the galaxy. The analogy is like watching airplanes in the sky. A distant jumbo jet, traveling at 500 miles per hour, seems to crawl across the sky because it is so far away. A nearby bird, traveling at only 30 miles per hour, zips past in an instant. The stars are like those jumbo jets. They are moving at tremendous speeds, often hundreds of thousands of miles per hour, but their immense distance makes their motion appear agonizingly slow from our perspective. Every star in our sky has its own proper motion, its own unique trajectory through the Milky Way. They are all like individual ships sailing on a vast, dark ocean, each with its own heading and speed. Our constellations are nothing more than a temporary alignment of these unrelated ships. We connect the dots from our vantage point on Earth, creating pictures of heroes and animals, but it is a cosmic illusion. The ships are all sailing on, and in time, the picture will dissolve. Let's return to the Big Dipper. In 50,000 years, its familiar shape will be gone. The stars in the handle and the inner bowl, which are part of a true moving group of stars, will have journeyed together across the sky. But the two stars at the end, Dubhe and Merak, which are not part of this group, will be left behind. The Dipper's bowl will have flattened out, and the handle will have become more bent. To our descendants, it might look more like a celestial fishhook or a spear. The same fate awaits all our constellations. Orion the Hunter will be disfigured. The stars that form his mighty shoulders, Betelgeuse and Bellatrix, are moving in different directions from the stars that form his belt and feet. Over 100,000 years, his body will be stretched and distorted until he is unrecognizable. Cassiopeia's wood shape will be warped into a jagged line. The Southern Cross will be no more. To witness this change, you need a time machine. You need to see 100,000 years pass in a minute. When you do, the sky comes alive. The stars, which seemed so still, begin to flow like a river. Patterns form and dissolve. Familiar shapes melt away and new, temporary alignments emerge. It is a silent, grand, and unending dance. It proves that our constellations are not eternal monuments. They are fleeting graffiti, written on the canvas of the cosmos, destined to be erased by the slow, relentless passage of time. We have seen the Earth wobble, changing our view of the heavens. We have seen the stars themselves drift, rewriting the constellations. But there is another, larger motion we must now consider, a journey that we are all a part of, every moment of our lives, the journey of our own sun. Our sun is not a stationary object at the center of the universe. It is a star, one of over 200 billion stars that make up our home galaxy, the Milky Way. And just as the Earth orbits the sun itself orbits a far greater center of mass, the monstrous, supermassive black hole that lurks in the heart of our galaxy, a cosmic titan known as Sagittarius A star. This is a journey of almost unimaginable scale. Our solar system is located in one of the Milky Way's spiral arms, about 27,000 light-years from the galactic center. To complete just one single orbit around that center, it takes our sun approximately 230 million years. This is a length of time so vast we call it a galactic year or a cosmic year. Think of it as a colossal, cosmic carousel. All the stars in the galaxy are on this ride, but not all are moving at the same speed. Stars closer to the center complete their orbits much faster, while those further out take longer. Our sun is just one of the billions of horses on this celestial ride, sweeping through space at a staggering speed of about 450,000 miles per hour, or 220 kilometers per second. We on planet Earth are along for the ride. This journey has profound implications for the sky we see. As we travel, we are constantly moving through different stellar neighborhoods. The stars that are our closest neighbors today will not be our neighbors in a few million years. We are like a ship sailing through an endless archipelago. The islands nearest to us are constantly changing. For example, Proxima Centauri is currently the closest star to our sun, a mere 4.2 light-years away, but it won't hold that title forever. In about 30,000 years, another small red dwarf star, Ross 248, will make a closer approach, coming within 3 light-years of us, before heading away again. Our sun's journey ensures that the cast of characters in our immediate cosmic vicinity is always being refreshed. Let's look back in time using this cosmic year. One galactic year ago, 230 million years in the past, the first dinosaurs were just beginning to walk the Earth. The continents were fused together into the supercontinent of Pangaea. The night sky they saw would have been utterly alien to us. The stars that form our constellations would have been in completely different parts of the galaxy. Since its birth, our sun has completed this grand orbit only about 20 times. It is a young traveler in an ancient city of stars. We know very little about the path it has taken. Has it passed through dense stellar clusters or near the remnants of ancient supernovae? How these past environments affected our solar system remains one of the great mysteries of our cosmic history. But one thing is certain, our journey continues. We are plunging into a new, unknown region of the galaxy, and the sky of the deep future will be a map of a place we have not yet been. So far, we have spoken only of motion, of the slow rearrangement of existing stars. But the sky is not a static collection of objects simply being shuffled around. It is a place of creation. The universe is constantly forging new stars, adding new points of light to the cosmic tapestry. The sky is not just changing, it is being born right now in colossal clouds of gas and dust. These places are called stellar nurseries, or molecular clouds, and they are among the most beautiful and awe-inspiring objects in the entire cosmos. They are vast, ethereal clouds of hydrogen gas and interstellar dust, spanning dozens or even hundreds of light years across. To the naked eye, they appear as dark patches in the Milky Way, obscuring the stars behind them, but through the lenses of powerful telescopes, like the Hubble or the James Webb, they are revealed to be vibrant, glowing canvases of cosmic creation. Imagine a cloud in our own sky. It is a diffuse, gentle thing. Now imagine that cloud was 1,000,000,000,000 times less dense, but so incomprehensibly vast that it contained enough raw material to build 1,000,000 suns. That is a stellar nursery. Within these cold, dark clouds, something miraculous happens. Gravity, the patient, persistent sculptor of the cosmos, begins its work. Over millions of years, gravity pulls the gas and dust together. It starts with tiny clumps, which grow larger and larger. As these clumps grow, their gravitational pull increases, and they begin to attract more material faster and faster. This is a process called accretion. It is a cosmic snowball effect. The core of these clumps becomes denser and hotter. Eventually, the pressure and temperature at the center of the collapsing clump becomes so extreme that a new fire is lit. The hydrogen atoms are fused together to create helium, releasing a tremendous amount of energy. A star is born. This newborn star unleashes a powerful stellar wind and intense radiation that blasts away the surrounding gas and dust, carving out a cavity in the nursery and revealing the brilliant new light to the universe. We can see this happening right now. In the constellation of Orion, just below the famous belt, is a fuzzy patch of light visible to the naked eye. This is the Orion Nebula, a stellar nursery just 1,300 light-years away. It is a stellar factory, actively forging thousands of new stars. The brilliant, hot young stars at its heart, known as the trapezium, are the ones illuminating the entire cloud, making it glow like a cosmic fluorescent light. These nurseries ensure that the stellar population of the galaxy is not finite. As old stars die, new ones are constantly being created to take their place. For every light that is extinguished, a new one is lit. A star that is born today in the Orion Nebula will one day drift out into the galaxy on its own journey. Perhaps in 100 million years, it will be a prominent feature in the night sky of a world we cannot yet imagine. The sky is not a finished piece of art. It is a canvas on which gravity is always painting. But for every act of creation, there is an equal and opposite act of destruction. The life of a star is a constant, invisible war, a titanic struggle between two fundamental forces: gravity, relentlessly trying to crush the star into an ever smaller point, and the outward pressure from the nuclear fusion in its core, pushing back against that collapse. For most of a star's life, these two forces are in perfect balance, a state of delicate equilibrium that can last for billions of years. But this balance cannot last forever. Eventually, the star's fuel will run out, and when it does, the war is lost. Gravity wins. For a star like our Sun, the end will be relatively peaceful. It will swell into a red giant, shed its outer layers to form a beautiful planetary nebula, and leave behind a dense, cooling ember called a white dwarf. It will fade away gracefully. But for stars far more massive than our Sun, stars containing the mass of 8 to 100 suns, the end is not graceful. It is the most violent and spectacular event in the universe. It is a supernova. When a massive star exhausts its fuel, its core can no longer fight against the crushing force of its own gravity. In less than a second, the core collapses catastrophically. It implodes at a quarter of the speed of light. The temperature skyrockets to 100 billion degrees. This collapse triggers a rebound, a shockwave of unimaginable power that blasts the star's outer layers into space at nearly the speed of light. The result is an explosion so brilliant, it can briefly outshine its entire host galaxy. A single dying star can unleash more energy in a few seconds than our Sun will in its entire 10 billion year lifetime. For a few weeks, a new dazzlingly bright star will appear in the sky, visible even in broad daylight, before slowly fading from view. This is not a theoretical event. We have seen them. In the year 1054, Chinese astronomers recorded the appearance of a guest star in the constellation of Taurus. It was so bright, it was visible during the day for 23 days. What they were witnessing was a supernova. Today, in that exact spot, we see the aftermath, the Crab Nebula, a tangled, expanding web of gas and dust, the ghost of a star that tore itself apart. A supernova, fundamentally and permanently changes the night sky. It removes a star from a constellation and leaves a beautiful, ghostly nebula in its place. More importantly, these explosions are the cosmic forges. The extreme energies in a supernova create all the heavy elements in the universe. Elements like gold, platinum, and uranium. This stardust is then blasted out into the galaxy, enriching the interstellar clouds that will one day form new stars and new planets. The iron in your blood, the calcium in your bones, the oxygen you are breathing, it was all forged in the heart of a dying star that exploded billions of years ago. A supernova is both a funeral and a birth announcement. It is the death of one star, but it is also the event that seeds the universe with the building blocks of new worlds and new life. But there are other, more fleeting changes to the night sky, visitors that come and go like ghosts in the starfield. Beyond the slow drift of the constellations and the rare cataclysmic violence of a supernova, the night sky is host to a menagerie of transient and temporary visitors. These are the celestial phantoms, objects that appear for a time and then vanish, reminding us that the heavens are not as static as they seem. For most of human history, these apparitions were seen as omens, divine messages, or harbingers of doom. Today, we know them as comets, meteors, and novae. Comets are perhaps the most famous of these celestial wanderers. They are what astronomers call dirty snowballs, clumps of ice, rock, and frozen gases, often only a few miles across. They spend most of their lives in the deep freeze of the outer solar system, in a vast, mysterious region called the Oort cloud, 1 trillion miles from the Sun. But occasionally a gravitational nudge will send one of these cosmic icebergs on a long journey into the inner solar system. As the comet approaches the Sun, the solar radiation begins to vaporize its ice. This releases a cloud of gas and dust called a coma, which can grow to be larger than the planet Jupiter. The solar wind then pushes this material away from the comet, creating its iconic, glowing tails. For a few weeks or months, the comet will be a beautiful, ethereal smudge of light in our sky, a ghostly visitor with a tail that can stretch for millions of miles. Then, as it swings back out into the cold darkness, it fades from view, perhaps not to return for thousands of years. As comets orbit, they leave a trail of dust and debris behind them. When the Earth passes through one of these trails, the tiny particles, often no larger than a grain of sand, burn up in our atmosphere at incredible speeds. This is a meteor shower. For a few hours, the sky is filled with dozens or even hundreds of shooting stars per hour. They are not stars at all, but the dying embers of a cosmic phantom's journey. Then there are the nova. A nova is a sudden, dramatic brightening of a star, but it is not a supernova. It is not the death of the star. A nova occurs in a binary star system where one star is a white dwarf, the dense, collapsed remnant of a star like our Sun. This white dwarf is a cosmic vampire. It uses its intense gravity to pull material, mostly hydrogen, from its larger companion star. This material builds up on the surface of the white dwarf until the pressure and temperature reach a critical point, triggering a runaway thermonuclear explosion on its surface. For a few days, the star system will flare up to be thousands of times brighter than normal, making a faint, invisible star suddenly appear as a new member of a constellation. Then it will slowly fade back into obscurity. The white dwarf survives the explosion and can repeat the process over and over again. These events, comets, meteors, and novae, are the short-term dynamic elements of our sky. They are the punctuation marks in the long, slow story of cosmic change. They remind us that the sky is not just a backdrop, but an active stage, with new actors, however brief their performance, constantly making an appearance. But all of this change, from the wobble of our planet to the explosion of a star, is happening on a much larger, moving canvas, a canvas that is itself expanding. In the 1920s, the astronomer Edwin Hubble was using the most powerful telescope of his time to study what were then called spiral nebulae. At the time, most astronomers believed that the Milky Way was the entire universe, and these fuzzy patches were simply gas clouds within our own galaxy. But Hubble made a discovery that would shatter that view and forever change our understanding of our place in the cosmos. He observed that these nebulae were not inside our galaxy. They were other galaxies, entire island universes like our own Milky Way, containing billions of stars, and they were located at immense distances, millions of light years away. But this was only his first revolutionary discovery. His second was even more profound. He noticed that nearly all of these distant galaxies were moving away from us, and the further away a galaxy was, the faster it was receding. The conclusion was inescapable. The universe itself is expanding. The analogy often used is that of a loaf of raisin bread baking in an oven. As the dough expands, all the raisins move further apart from each other. From the perspective of any single raisin, all the other raisins would appear to be moving away from it. There is no single center to the expansion. The expansion is happening everywhere at once. The galaxies are the raisins, and the fabric of space-time is the dough. This expansion of the very canvas of the cosmos has a startling and melancholic implication for the deep future of our night sky. As the distant galaxies are carried away from us by the expansion of space, their light has to travel across an ever-increasing distance to reach us. This stretches the light, a phenomenon called cosmological redshift. More importantly, there is a speed limit in the universe, the speed of light. If a galaxy is far enough away, the space between it and us can be expanding faster than the light from that galaxy can travel towards us. Imagine trying to run up a downward moving escalator. If the escalator is moving down faster than you can run up, you will never reach the top. You will be carried away. In the same way, the light from these distant galaxies will never reach us. They will cross a cosmic event horizon, an observational point of no return. This means that, over billions of years, the night sky will slowly empty. One by one, the distant galaxies will recede, and their light will redshift into oblivion. They will wink out of our view, forever. In the unimaginably distant future, 1 trillion years from now, our own Milky Way and its nearby neighbors in the local group will have merged into one supergalaxy. But beyond that, the sky will be black, empty. All other galaxies will have been carried away beyond our cosmic horizon. Future astronomers on a distant Earth will look out into a universe that appears to be composed of only one single galaxy, their own, surrounded by an endless, eternal void. They might never know that a rich, vibrant cosmos of billions of other galaxies ever existed. The story of the universe would be lost to them, erased by the relentless expansion of space-time itself. This is the ultimate change to our night sky. Not just the rearrangement of its parts, but the slow, majestic, and final disappearance of the canvas itself. Even as the distant galaxies are carried away from us on the tide of expanding space, our own cosmic home, the Milky Way, is undergoing its own slow, profound transformation. Our galaxy is a vibrant, bustling city of stars, its spiral arms glowing with the light of hot, young blue stars, and painted with the pink and crimson hues of active star-forming nebula. But cities change. They age, and our Milky Way is on a one-way path towards a quiet, stellar retirement. The engine of a galaxy's vibrancy is its supply of gas. This interstellar gas is the raw material from which new stars are born, but this supply is finite. Every time a star is born, some of that gas is locked away. While massive stars return some of this material to the galaxy when they explode, much of it remains trapped in smaller stars and stellar remnants. Over billions of years, the galaxy is slowly but inexorably using up its creative potential. Imagine our galaxy is a great cosmic bonfire. The spiral arms are the brightest, hottest parts of the fire, where the fuel is being consumed most rapidly. But the pile of wood is not infinite. As the fuel is used up, the fire will begin to die down. The brilliant, hot-burning flames will be the first to go, leaving behind the slower-burning, redder embers. In about 5 to 7 billion years, around the time our own sun begins to die, star formation in the Milky Way will have slowed to a trickle. The beautiful nebulae, like Orion and Carina, will have faded, their gas either consumed or blown away. The brilliant, blue supergiant stars that currently adorn the spiral arms will be long gone, having lived their short, spectacular lives. Without new stars to light them up, the iconic spiral arms themselves will fade into invisibility. The galaxy will transition from a vibrant blue and pink spiral into a quieter, yellower, and eventually redder collection of aging stars. The stellar population will be dominated by long-lived, dim red dwarfs, the celestial embers of our analogy. These stars are incredibly fuel-efficient, sipping their hydrogen so slowly they can live for trillions of years. They will be the last lights to go out in the universe. As we journey into this distant future, 100 billion years from now, the Milky Way would be unrecognizable. It would be a dim, ghostly disk of ancient red stars, drifting in an immense and silent void, the light from all other galaxies having long since departed from our sky. It would be a galaxy of survivors, a quiet testament to a more brilliant, youthful past. But before this slow fade into darkness, our galaxy is destined for one last, violent, and spectacular act of transformation. A celestial cataclysm is bearing down upon us, a dance of titans that will rewrite the very architecture of our sky. While nearly every galaxy in the universe is rushing away from us, there is one major exception. The great Andromeda Galaxy, our closest spiral neighbor, is hurtling towards us. It is a cosmic monster, possibly containing 1 trillion stars, significantly more than our own Milky Way, and it is approaching us at a speed of nearly 70 miles per second, or about 250,000 miles per hour. It is not being carried away by the expansion of space, because our mutual gravity is strong enough to overcome it. We are locked in a gravitational embrace, a slow-motion fall towards one another that has been unfolding for billions of years. In approximately 4.5 billion years, this slow fall will end. The Milky Way and Andromeda will collide. Now, the word collision conjures images of destruction, of planets and stars smashing into one another. But space is defined by its emptiness. The distance between stars is so vast that when two galaxies merge, the stars within them will almost certainly not collide. The analogy is not two bullets hitting each other, but rather two immense swarms of bees flying through one another. While the swarms will merge and become one, it is incredibly unlikely that any two individual bees will ever touch. But while the stars will survive, the galaxies as we know them will not. The collision will be a gravitational masterpiece of chaos and creation. As the two galaxies first pass through each other, their structures will be torn apart by immense tidal forces. Great streamers of stars and gas, hundreds of thousands of light years long, will be flung out into the void, creating vast arcing tidal tails. Our familiar graceful spiral arms will be stretched, warped, and utterly destroyed. From the perspective of a future Earth, the night sky during this period would be a sight of unimaginable splendor and terror. Andromeda, which is now a faint, fuzzy patch of light, would grow over millions of years to fill the entire sky. As the galaxies merged, the familiar band of the Milky Way would be replaced by new chaotic rivers of stars, vast curtains of light, and dark dust lanes from Andromeda's core. The sky would be a swirling, violent canvas, a front-row seat to the remaking of a galactic home. The two supermassive black holes at the hearts of both galaxies would begin a long, spiraling death dance, orbiting each other for millions of years before finally merging in a cataclysmic event that would send gravitational waves screaming across the fabric of space-time. This collision is not an attack. It is a merger, an act of galactic cannibalism that will give birth to a new and very different type of galaxy. After the initial chaotic pass-throughs and the violent gravitational stripping of their structures, the Milky Way and Andromeda, along with their smaller satellite galaxies like Triangulum, will spend the next few billion years settling down. Their stars, once residents of separate cosmic cities, will mingle and mix until they form a single, colossal new entity. Astronomers have given this future galaxy a nickname, Milkomeda. Milkomeda will not be a beautiful spiral like its parents. Galactic mergers of this scale tend to destroy the delicate spiral structures. Instead, it will be a giant elliptical galaxy, a vast, football-shaped swarm of stars, much larger and more massive than either the Milky Way or Andromeda were alone. The collision will have one last, spectacular side effect. The merging of the two galaxies will slam together their vast reserves of interstellar gas. This collision of gas clouds will trigger a final furious burst of star formation, a galactic starburst. For a few 100 million years, Milkomeda will blaze with the light of trillions of newborn stars. The night sky from a planet within this new galaxy would be utterly transformed. The familiar, relatively sparse starfield we know would be gone. In its place would be a sky saturated with light. The density of stars, particularly near the new galactic core, would be immense. The sky would have no truly dark patches. It would be a dome of near-continuous starlight, brighter than a full moon on Earth today, every single night. New, brilliant nebulae, larger and brighter than any in our current sky, would glow across this celestial sphere. It would be a sky of breathtaking beauty, a temporary renaissance of light and creation born from the wreckage of two former galaxies, but it would be a final, glorious flash before the long decline. This starburst would rapidly consume the last of the available gas, the final fuel in the galactic tank. After this burst is over, star formation in Milkomeda will cease forever. The galaxy will then begin its slow, inevitable journey into old age. The hot blue stars from the starburst will die out. The nebulae will fade. Over hundreds of billions of years, Milkomeda will slowly redden, its light dominated by the ever-growing population of ancient, dim, red dwarf stars. The sky, once a chaotic blaze of glory, will become progressively dimmer, sparser, and colder. It will be the beginning of the true twilight of the cosmos, an era not of stars but of their ghosts. We now journey forward in time, so far into the future that the numbers lose their meaning. We travel to an age 100 trillion years from now. By this point, the expansion of the universe has carried all other galaxies beyond our cosmic horizon. The great merged galaxy of Milkomeda is alone in the observable universe. Star formation ceased long ago, and now the very last of the stars are beginning to die. The last lights to go out will be the red dwarfs. Having sipped their fuel for trillions of years, even their impossibly long lives must come to an end. One by one, they will flicker out, leaving behind not a supernova, but a quiet, cooling white dwarf. Eventually, the last red dwarf will exhaust its fuel, and the last star in the universe will go dark. The stelliferous era, the age of stars, will be over. The universe will enter a new, profoundly different epoch, known as the degenerate era. The cosmos will now be populated only by the corpses of stars, the stellar remnants. There will be brown dwarfs, failed stars that never ignited. There will be white dwarfs, the dense cores of stars like our sun, slowly cooling from white-hot to black, becoming cold, dead diamonds of crystallized carbon and oxygen. There will be neutron stars, the ultra-dense cinders of supernovae, spinning silently in the dark. And there will be black holes, the gravitational tombs of the most massive stars. The universe will be almost completely dark. The analogy is a city after a total power failure. All the lights are out. The only things that remain are the cold, dark buildings. The planets will still orbit their dead suns, frozen worlds bathed in a darkness more profound than any we can imagine. Occasionally, two of these stellar remnants will spiral into each other, creating a brief final flash of light in the form of a supernova, a final lonely firework in an otherwise eternal night. The primary source of energy in the universe will no longer be fusion, but annihilation. Matter and antimatter will occasionally meet, converting directly into energy. But these events will be extraordinarily rare. The universe will become a place of immense, cold, and almost perfect emptiness, populated only by these scattered stellar ghosts. It is an era of unimaginable patience, where time itself seems to almost lose its meaning. But even these ghosts are not eternal. For in the deep future, the very laws of physics conspire to erase even the memory of matter itself. Our journey now takes us to the furthest, most speculative shores of theoretical physics. We enter a timescale so vast that it makes the age of the stars seem like the blink of an eye. We are contemplating the end of matter itself. According to some of our most advanced theories, the grand unified theories, protons, the fundamental building blocks of atomic nuclei, are not perfectly stable. They are predicted to decay, but their half-life is astronomically long, on the order of 10 to the power of 36 years, a 1 followed by 36 zeros. It's a number so large that if you were to wait for a single proton in your body to decay, you would have to wait trillions of times the current age of the universe. But in the deep future, time is no longer a constraint. Over these unfathomable timescales, the stellar remnants that populate the degenerate era will slowly, proton by proton, dissolve into a bath of low-energy radiation and subatomic particles. The cold black dwarf stars, the neutron stars, all of it will slowly sublimate into nothingness. It is the ultimate erosion, the universe slowly erasing itself. The only objects that will remain are the black holes. These gravitational monsters seem eternal, but even they are not forever. In 1974, the physicist Stephen Hawking proposed a stunning theory. Due to quantum effects near their event horizons, black holes should slowly leak radiation back out into the universe. This is now known as Hawking radiation. This process is a form of evaporation. It is incredibly, mind-bogglingly slow. A black hole with the mass of our sun would take 10 to the power of 67 years to evaporate. The supermassive black holes at the centers of galaxies, like the one that will form in the heart of Milkomeda, could take as long as 10 to the power of 100 years, a number known as a googol. As a black hole evaporates, it loses mass, and the process speeds up. In its final second of life, it will unleash all its remaining energy in a final, tremendous flash of gamma rays. A final, definitive statement in the silent, empty cosmos. One by one, from the smallest to the largest, every black hole in the universe will evaporate away. And with the death of the last black hole, the universe will enter its final, hypothetical state, the heat death. It will be a vast, ever-expanding sea of low-energy photons, neutrinos, and other fundamental particles, all spread so thin that the chance of any two of them interacting is virtually zero. A universe of perfect equilibrium. A universe where there is no more change, no more structure, no more complexity. Nothing will ever happen again. It will be the final, silent, and eternal night. We have journeyed from the subtle wobble of our planet to the final evaporation of a black hole. We have watched constellations dissolve, galaxies collide, and the universe itself fade into a cold, dark void. It is a story of change, on a scale that is both humbling and terrifying. It proves that nothing, not the stars, not the galaxies, not even matter itself, is permanent. The only constant in the cosmos is transformation. But this journey into the deep future teaches us something profound about the present. It forces us to return to this very moment, to the here and now. The night sky that you can see tonight is a unique and precious arrangement. The patterns of the constellations, the faint glow of the Andromeda galaxy, the river of our own Milky Way, it is a celestial portrait that has never existed before in exactly this way, and will never exist again. You are living in the stelliferous era, the brief, glorious morning of the universe, when the cosmos is ablaze with the light of creation. You are witness to a fleeting masterpiece. So the next time you are outside on a clear night, look up, appreciate the view. See the stars not as fixed, distant diamonds, but as fellow travelers on an extraordinary journey. Know that you are seeing a single frame in the grandest motion picture of all time. A picture of a dynamic, evolving, and living cosmos. A picture that is yours and yours alone for this brief, brilliant moment in forever.